The 2017 Nobel Prize in Physics recognized Weiss, Barish, and Stephen Thorne for the detection of gravitational waves, a groundbreaking achievement that confirmed a key prediction of Albert Einstein's general theory of relativity and opened a new window onto the universe. This essay will explore the historical context leading to this momentous discovery, the construction and operation of the Laser Interferometer Gravitational Wave Observatory, known as LIGO, the interpretation of the detected signals and the profound implications for astrophysics and cosmology. The genesis of gravitational wave research lies in Einstein's 1916 formulation of general relativity, which reimagined gravity, abandoning the Newtonian concept of a force acting at a distance. Instead, general relativity describes gravity as a curvature of spacetime caused by mass and energy. Einstein predicted that accelerating massive objects would create ripples in this spacetime curvature, propagating outward as gravitational waves at the speed of light. These waves compress and stretch space in orthogonal directions as they pass, a subtle but profound effect. While Einstein initially entertained doubts about their detectability, the theoretical groundwork was solid. The quest to detect these elusive waves began in earnest in the mid-20th century. Joseph Weber, at the University of Maryland, pioneered the first generation of gravitational wave detectors, resonant mass antennas composed of large aluminum cylinders. Weber hypothesized that a passing gravitational wave would cause the cylinder to vibrate, which could then be detected by piezoelectric transducers attached to the cylinder's surface. While Weber claimed initial detections in the late 1960s, his results were disputed by other research groups, and his detectors lacked the sensitivity required to confirm gravitational wave events definitively. The scientific community ultimately deemed Weber's observations inconclusive. Despite the skepticism surrounding Weber's early claims, his efforts played a crucial role in galvanizing interest in gravitational wave detection and inspiring subsequent generations of scientists. Weiss, in particular, recognized the limitations of resonant mass antennas and began exploring alternative detection methods. He proposed the concept of using laser interferometry to measure the minute changes in distance induced by gravitational waves. This idea formed the foundation for LIGO. The principle behind LIGO is elegant in its simplicity. LIGO consists of two L-shaped detectors, one in Hanford, Washington, and the other in Livingston, Louisiana. Each detector features two arms, 4 kilometers in length. Arranged at right angles, a laser beam is split into two, with each beam travelling down one of the arms, reflecting off a mirror at the end, and returning to the starting point where they recombine. If a gravitational wave passes through the detector, it will slightly alter the length of each arm, one arm stretching while the other contracts, and then vice versa. This change in arm length is infinitesimally small, far smaller than the size of an atom, yet detectable due to subtle changes in the interference pattern when the two laser beams recombine. The difference in path length is measured with extreme precision using techniques involving the wave nature of light. The construction of LIGO represented an enormous engineering and technological challenge. The detectors demanded unprecedented levels of stability, requiring sophisticated vibration isolation systems to shield the mirrors from seismic noise and other disturbances. The lasers had to be incredibly powerful and stable, with their frequency precisely controlled. Moreover, the vacuum inside the arms had to be nearly perfect to eliminate any interference from air molecules. The entire system operated under strict environmental control to minimize thermal fluctuations. Weiss focused on the detector design and noise reduction strategies, recognizing that overcoming environmental disturbances was paramount. Thorne provided the theoretical framework for understanding the expected gravitational wave signals and their interaction with the detectors, including waveform modeling that predicts the signal shape from various astrophysical sources. Barish was instrumental in transforming LIGO from a prototype into a fully operational, large-scale scientific collaboration. His leadership ensured the project stayed on track and attracted the necessary funding and expertise. On September 14, 2015, after decades of development and refinement, LIGO achieved its historic breakthrough. Both detectors simultaneously registered a signal consistent with a merger of two black holes, with masses approximately 29 and 36 times the mass of the Sun, located 1.3 billion light-years away. The detected signal, designated GW 150,914, lasted a mere fraction of a second, rising in frequency and amplitude, a characteristic pattern known as a chirp. Analysis of the signal revealed that the merger resulted in a single black hole with a mass of about 62 solar masses. The remaining energy, equivalent to about 3 solar masses, was radiated away as gravitational waves, traveling across the cosmos to reach the detection of GW 150,009 Info 14 provided compelling evidence for the existence of black holes and confirmed a major prediction of general relativity. It validated the ability of LIGO to detect gravitational waves from cataclysmic astrophysical events, heralding a new era of gravitational wave astronomy. Subsequently, LIGO and its sister observatory, Virgo, located in Italy, have detected numerous other gravitational wave signals from black hole mergers, neutron-star mergers, and even a black hole neutron-star merger, each providing unique insights into the nature of these exotic objects and the dynamics of strong gravitational field. The detection of gravitational waves has profound implications for our understanding of the universe. Gravitational waves offer a complementary perspective to traditional electromagnetic observations, providing information about astrophysical objects and events that are invisible to telescopes. For instance, black hole mergers are virtually silent in the electromagnetic spectrum, but they produce strong gravitational wave signals. Similarly, gravitational waves can probe the interiors of neutron stars, providing information about their composition and equation of. Furthermore, gravitational waves can be used to test general relativity in extreme gravitational environments, probing the limits of Einstein's theory and searching for deviations that might point to new physics. The study of gravitational waves also holds the potential to shed light on the early universe, revealing information about the inflationary epoch and the formation of the first structures. The success of LIGO has spurred the development of advanced gravitational wave detectors, including upgrades to LIGO and Virgo, as well as the construction of new detectors in Japan, India, and Australia. These advanced detectors will be more sensitive and will be able to detect gravitational waves from even more distant and fainter sources. In addition, space-based gravitational wave detectors, such as those interferometer space antenna, known as LISA, are being developed to detect gravitational waves at lower frequencies than ground-based detectors, opening up new possibilities for exploring the journey to detect gravitational waves was a long and arduous one, spanning decades of theoretical and experimental work. The perseverance, ingenuity, and dedication of Rainer Weiss, Barry Clark Barish, and Kip Stephen Thorne, along with the contributions of countless other scientists and engineers, culminated in a remarkable achievement that has revolutionized our understanding of the universe. Their work stands as a testament to the power of scientific collaboration and the transformative potential of fundamental research. The era of gravitational wave astronomy has dawned, promising to unveil new mysteries and reshape our view of the cosmos. The meticulous engineering, the theoretical breakthroughs, and the collaborative spirit combined to unlock a new sensory modality for the universe. This achievement transcends a mere confirmation of Einstein's theory. It represents a fundamental shift in how we perceive and investigate the cosmos, ushering in an unprecedented era of scientific discovery.